Next topic, so mechanics of materials, model 1. So next topic is on stress strain relationship. So first, for that we should know about the elastic limit. So when an external force acts on a body, the body tends to undergo some deformation. If the external force is removed, the body comes back to its original shape and size. The body will regain its original shape and size only when the deformation caused by the external force is within a certain limit. The value of the force corresponding to the limit is called limiting force. The value of stress corresponding to the limiting force is called the elastic limit of the material. Means suppose when a load is applied, as we know, for everything, when a load is applied, mainly for ductile materials, it undergoes deformation or elongates up to some limit. So when the load is removed, it comes back to its original position. So that's elasticity, as we clearly know that. But when the but there exists a one limit to which the so this limit is nothing what is called as the elastic limit, and the corresponding force to that is called as elastic limiting force, and the corresponding stress is called as the elastic limit of that material. Hooke's law. It states that when a material is loaded within an elastic limit, the stress is directly proportional to the strain. So stress is directly proportional to the strain. So within the elastic limit, up to the elastic limit, Hooke's law states that when the material is loaded within the elastic limit, the stress is directly proportional to strain. And if it is written in a mathematical way, that constant stress is directly proportional to strain, which is replaced by constant. So this constant is known as Young's modulus. Young's modulus is nothing but ratio of stress by strain, sigma by epsilon. So Young's modulus is given by capital E, stress is sigma, strain is epsilon. So Young's modulus is stress by strain or sigma by epsilon. So as we know that stress is F by A, and strain is the word change in length upon original length. So L by dl is equals to E, or we can rewrite the formula as change in length delta L equals to FL by AE, the most the most widely used formula to find the change in length. Delta L equals to FL by AE. Next topic is Poisson's ratio. Before going ahead to the stress strain relationship, first we'll know about the Poisson's ratio. When a body is subject to direct stress, it undergoes deformation in the direction of load, as you can see in the figure, and perpendicular to the load, there is an increase in length in the direction of load and decrease in lateral dimension as shown in the figure. So as shown in the figure, the solid lines is the material before loading, and the dotted lines is the shape of the load or material after loading. So as you can see, it is decreased in lateral way and it is increased in the longitudinal way along the force. Also, as you can see from the sideways, the it has the square, the solid lines are the original square. So dotted square is the shape after elongation of by the force. So the ratio of the lateral strain to longitudinal strain is defined as Poisson's ratio. So it is the ratio of lateral strain to linear or longitudinal strain is defined as the Poisson's ratio. It is denoted by 1 by m or nu. The value of m mostly most material lies between 3 to 4. It means that one third or one fourth. It can reduce to one third or one fourth. So Poisson ratio 1 by m is lateral strain upon longitudinal strain, or Poisson ratio mu is capital D minus small d upon d for depth, or for the breadth is B capital B minus small b upon b. So next topic, that's very important, stress strain relationship for mild steel. The mechanical properties are commonly determined from a standard tensile test. A tensile testing machine called the universal testing machine, also called as UTM. This test consists of gradually loading a standard specimen of a material and noting the corresponding values of load and elongation until the specimen fractures. The load is applied and measured by a testing machines. The stress is determined by dividing the load values by the original cross-sectional areas of the specimen. The elongation is measured by determining the amount of two reference points on the specimen that are moved apart. Original distance between the two reference points is known as the gauge length. The strain is measured by dividing the elongation values by the gauge length. As we know that strain is change in length by original length. So the values of stress and corresponding strains are used to draw the stress strain diagrams of the material used. The following figure shows the stress strain diagram of a mild steel. So various properties are discussed below. So here, for any material to test its capabilities or its properties, mechanical properties, we use a universal testing machine called as a UTM. So on this UTM, a specific specimen of that material is made to test on the UTM machine. So before testing, the original area of the specimen and the gauge length, the length to be gauge length or the length of the specimen is measured. Then so after the test is carried out, so every load is divided by the original cross-sectional area, which gives a stress at different points. So plotting those points on the y-axis, that is stress, and plotting strain on the x-axis, that is change in length by original length at every point, or elongation at every point is measured and plotted along x-axis, that is strain. So we get this graph. So this is called a stress strain graph. So as you can see the curve. So this curve is for the mild steel specimen on the UTM machine. So we have some critical points. So this first point is point P, then point E, then point YU, then YL, then point Y, the point U at the top, and lastly the point B at the end. So I'll discuss one by one the features of this stress strain diagram. First is proportionality limit. Also, so from point O, start from the initial point O below, from the origin from O to P, the curve is a straight line, that is stress is directly proportional to the strain. Therefore, it is clear that Hooke's law holds good up to this point P, and this point P is known as the proportional limit or proportionality limit. So in this proportionality limit, the stress is directly proportional to strain. Means here the Hooke's law is good at till this point. As you can see in the figure, from the origin O to the point P, the straight line is called as proportionality limit. Now elastic limit. So up to the point E, from O to E, from the origin to E, the material will regain its shape and size when the load is removed. It means that the material has elastic properties up to point E. This point is known as the elastic limit. These 2 points are very close enough to differentiate. So these two almost are proportional limit and elastic limit are almost the same thing because they both are same. Next, yield point. So yield point, that is, there are three different yield points: YU, YL and Y. So yield point, if the material is stressed beyond the point E, plastic stage will reach, that is, on the removal of the load, the material will not be able to recover from its original shape and size. At the point YU, there is an increase in strain without appreciable increase in load. Thus, the curve of the curve drops to the point YL. Then again, the strain increases, and the stress is practically constant up to point Y. This phenomenon of increase in strain without any appreciable increase in load is called as yielding. So this yielding, we can hear a sound on the testing machine while connecting the test. So this sound is nothing but the yielding point. This point is nothing but yielding point. The point YU is called the upper yield point, and the point YL is called lower yield point. And practically the lower yield stress is more important, as this point is called as the yield point. The stress at the yield point is called as yield strength. The yield point is so near to the elastic limit that for that, so most of the purpose the stroke taken as a 1. So these points are very near to all. So elastic yield point, elastic points are taken as the same. Now comes the ultimate point. So between the point Y and U, upper point of U, the ductile extension or elongation takes place, or plastic region. This is a plastic region, and elongation takes place. The relation between stress and strain depends on the rate of loading also. So during the extension, the cross-sectional area decreases uniformly over the length such that the volume remains constant. So at the point U, the stress attains a maximum value, which is known as the ultimate point. The stress at this point is known as the ultimate stress or ultimate strength. So this is defined as maximum stress obtained by dividing the maximum value of load reached to the original area of the specimen. So this is the maximum point, a maximum stress, a maximum height a material can reach, showing its maximum strength to hold the load. So at this point shows what the maximum load a metal can handle. So lastly, the breaking point, that is point B on the last point B on the stress strain diagram. So after the maximum load is reached, local yielding takes place and a neck or waist is formed. As the cross-sectional area decreases considerably, the load carrying capacity of the specimen decreases. Hence, the portion UB, the strain increases for decreasing stress. Even though the normal stress is decreasing, the actual stress, which is equal to the load divided by the actual cross-sectional area at neck, will be continuously increasing. So at the point B, the specimen breaks. The stress at this point is called the breaking stress, and corresponding load is called the breaking load. The nature of the fracture from milestone will be in form of cup and cone. So after breaking, the specimen will be in the form of cup and cone at the broken ends. So this was about the Explanation of stress relation for mild steel, very important tool for an engineering student to know about the stress relations. So next, stress strain relationship for the materials including non-ferrous metals. So we have so the stress were already conducted, and the graphs are shown in the above figure. Stress strain graphs are shown for different materials. So here the graph is shown for different percentage of carbon content. So as we know, so each every every steel has carbon contents. So based on the carbon contents, so we have the different stress strain curves. So the first curve is of 0.12% of carbon present in iron. The next curve is 0.25% of carbon in iron. Third is 0.5% of carbon in iron. Fourth is 0.8% of carbon in iron. And fifth is 0.1% of carbon in iron. Suppose figure shows stress strain curve for steel having carbon content. Suppose 0.12 to 1%. So as you can see that with higher carbon content, it is similar to a brittle material even though ultimate stress is much higher. So with higher carbon content, the ultimate stress will increase, but the material will change its form from ductile to brittle as we keep on adding the carbon content. So next figure shows different types of materials. So above figure shows stress strain diagram for common metals such as high carbon steel, first one above. Next is nickel, chromium steel, mild steel, wrought iron, cast iron, copper and cast aluminum. So for this it is noted that steel and wrought iron the proportionality exists almost until the yield point. For copper, iron, aluminum, proportionality limit or yield point behaves like there is no clear or defined proportionality limit or yield point. Cast iron behaves like a brittle material which fails without any visible elongation.